Hello, good morning everyone. Dr. Bennett here. Today we're going to have a look at deriving the Breguet endurance equation specifically for a jet-powered airplane. So to start this derivation, we have to go back to the so-called average value method for endurance, which states that endurance is the amount of fuel that we have to burn. So this is the fuel load, delta WF, divided by the rate at which we're burning through that fuel. So this dot notation here is shorthand essentially for a derivative with respect to time. So W dot F just means dWF by dt. So for example, if we have a fuel load given in units of kilograms and our rate of fuel burn is, for example, kilograms per hour, the units of this equation will simplify to kilograms over kilograms per hour, giving us an endurance in hours. So that's the so-called average value method. We can progress this if we use our equation for the thrust-specific fuel consumption C sub T, which is the rate of fuel burn divided by the thrust itself. Now, for a cruise problem, like this endurance problem, we are assuming that our thrust is equal to drag if we are cruising at a constant speed, right? So if thrust is greater than drag, then we would accelerate, and if drag was greater than thrust, then we would decelerate. So if we're at constant speed, then thrust is equal to drag, and likewise, if we're at constant altitude, then lift is equal to weight. So specifically what that means for this formulation is that we can just replace WF dot with delta WF. So if thrust is equal to drag, then this just becomes this, right? So that's where we're going to start with our derivation of the Breguet equation. The problem with the average value method, this formulation right here, is that it doesn't take into account the fact that as the weight of the aircraft reduces as we burn fuel, the speed that we should trim at in order to achieve maximum endurance should also change. And that comes from just basically looking at the lift equation. So the magnitude of lift is the lift coefficient multiplied by dynamic pressure multiplied by the wing reference area S. So just expanding this, dynamic pressure half rho v squared S. And from our cruise problem formulation here, lift we're saying is equal to weight if we are at constant altitude. So essentially, V, airspeed, is a function of W. So if we rearrange this equation like that, that tells us that as the weight of the airplane reduces, then the speed at which we should trim at in order to achieve maximum endurance should also reduce. And that's the problem with the average value method. It doesn't take that into account. So what we're going to do to extrapolate this into the Breguet method is say that endurance is equal to an integral. So instead of using this delta WF term in the numerator, we're just going to integrate this term with respect to W instead. And one last thing that I need here is, because if W1 is our starting weight and our W2 term is our ending weight, W2 is always less than W1, isn't it? So we're always burning fuel. We need a negative sign right there. So if we make this integration, we should arrive directly at the Breguet equation for endurance, specifically for a jet. So the first thing I'm going to do here, as you will have seen in the previous videos regarding a piston propeller driven airplane, is to use our little mathematical trick and essentially multiply this inside of the integral by 1 in disguise. So let's do that over here. So if lift equals weight in our cruise problem, then L over W is equal to 1. So what I'm going to do is just multiply this term inside the integral by 1 in disguise. So to get us started, 1 over CT, L over D, 1 over W dW. So then what I can do is take out all of the terms outside of the integral that don't depend on W. So that is all of this stuff here. So I'm going to take that stuff outside of the integral. That stuff doesn't depend on W. And so that will lead me to, I'm also going to write the magnitude of lift and magnitude of drag in coefficient form, just to make this equation a little bit more generic as well. So I'm going to get that, right? I can do that because the lift and drag coefficients, well, the magnitudes are non-dimensionalized into coefficients as a function of Q and S. So the Q and S's would cancel in the numerator and denominator anyway, so I can do that. And then I've just got a very straightforward integral to calculate here. So let's just do that real quick. Natural log, right? The integral of 1 over W with respect to W is the natural log of W evaluated between W1 and W2. And then this leads me directly to the Breguet endurance equation. So T CL over CD log of W2 subtract log of W1. I can tidy this up just a little bit. I can push this negative sign into the bracketed term on the end, right? The CD. So I'm just going to flip this around like that. And then using the law of natural logarithms, I can do like that, right? So this is the Breguet endurance equation for jet-powered airplane specifically. Quite a straightforward equation, right? So to achieve the objective of maximizing endurance, I need to minimize my thrust-specific fuel consumption. That makes sense, right? Minimizing fuel consumption will maximize endurance. That's going to give us the longest possible amount of time in the air. And I also need to maximize my lift to drag ratio directly. So this is the direct lift to drag ratio, and as we discussed in the previous video regarding the Breguet equations for piston propeller driven airplanes, the maximum lift to drag ratio is achieved when the parasite drag CD0 is equal to the induced drag KCL squared. So one last thing to cover up then before we complete this series of videos, and that will be the Breguet range equations for jet-powered airplanes, so stay tuned for that one. Thank you.